The question I have here is, could you do an example on the calculation of strains? In this example, I'll consider variable strain, strain that varies with distance. Here's the problem. We have a one-dimensional rod with a constant cross-section throughout. Defining the x-axis starting from point A like shown in the picture, the rod is subjected to a distributed load in the x direction. Further analysis indicated that the displacement of the rod at various points in the x direction is a function of x given by this particular function. And here c is a constant whose value is given, and L is the length of the rod, which of course is 2 meters. The question is to determine the normal strain at point A, the normal strain at point B, and the average normal strain in the rod. Since u is a function of x, we have to use the calculus definition of the normal strain epsilon, which is this. The strain in the x direction equals the first derivative of the displacement u with respect to x. A side note is that in two-dimensional problems, u will be a function of x and y, and then in that case, this will be a partial derivative as opposed to an ordinary derivative. So I took the derivative of this function with respect to x. C remains outside the parenthesis as a constant, and this term, when differentiated with respect to x, becomes L, and this term, right, becomes simply x. Why? Because x squared differentiated with respect to x would be 2x, right? So that 2 and 2 will cancel out. We end up with simply x. When you run into functions like this, it always pays to spend some time and understand the nature of the function. And here we note that we have a linear function. In other words, epsilon varies linearly with x. You can see this is sort of like y equals mx plus c kind of function, right? So if we have two values, all we have to do is to connect the two values by a straight line. We have a variation of the strain within the rod, right? The logical choice for these 2 points would be points A and B. So here I am calculating the corresponding values of the strain at these points. X equals 0, so all I have to do is to substitute x equals 0 in this equation. I get epsilon equals c times L, and at x equals L, you can see this term becomes 0, and therefore epsilon is 0. And therefore the strain varies from its maximum value at point A to 0 at point B. Now you can see it's very easy to answer the questions. The strain at point A is c times L. You substitute the numbers and you get 16 times 10 to the minus 4. Remember, strains don't have any dimension. This is confirmed by the fact that we end up with no units here. Meter to the power of minus 1 multiplied by meter gives you no units. Now you take this number and multiply that by 100 to express this as a percentage. So you get 0.16%. The strain at point B is 0. Since the strain varies linearly, all we have to do is to take the two values at the ends of the rod, average them out in order to find the average strain for the whole rod, right? So here you get a value of 0.08%, which is the value in the middle of the rod, right here. But if the strain is not linear, then you have to use calculus to find the average. So let's illustrate that here so that you can apply this in problems where the strain is not linear. Since epsilon varies with x, we would typically use what is called the length-based average. Here is the equation for that. You simply say epsilon average times L must be equal to integral of epsilon times dx going from 0 to L. Now you substitute this function for epsilon, integrate and apply the limits. E average times L therefore works out to be CL squared over 2, and therefore E average is simply CL over 2. We get the same value of 0.08% for E average as in the first method.